So here's what I'm going to do today. We're going to start in section 1.1. There'll be a lot of review, I'm sure, for a lot of people here, but we'll start in on section 1.1 and we'll just move on from there. Okay. All right, so section 1.1 is on functions and function notation. Now, before we hit the idea of functions, the first concept that comes up is the concept of a relation. All right? In mathematics, a relation is a correspondence between inputs and outputs. So a set of inputs and a set of outputs. Any set of inputs, mathematically, it's called the domain. The set of outputs is called the range. Okay? So any correspondence whatsoever is a relation. As long as we have inputs and outputs, we have a relation. Okay. Now, there's a lot of different ways I can see a relation. There's a lot of different notations that we're going to look at. The first one that a lot of people get introduced to is this, what I call bubble notation. All right? With bubble notation, we have one bubble that denotes the domain and another bubble or circle or ellipse that denotes the range. And here we see that the relation sends the input of A to the output of 2. It sends the input of B to 1. It also sends the input of B to the number 3. And then it sends the input of C to the number 3 as well. Okay. Now it turns out just because of the space requirements that it takes to create bubble notation, we quickly go to different types of notations, like arrow notation and ordered pair notation. Just because it takes less space out. Arrow notation is where each input has an arrow going out from it and sending it to an output. So in our previous bubble notation, in arrow notation, I could have said A is sent to 2, B is sent to 1, B is also sent to 3, and C is sent to 3. With ordered pair notation, I can do the same thing. With ordered pair notation, the first element is always the input, and then a comma, and then the second element is the output. So again, in that relation we just looked at, A comma 2 means A is sent to 2. B comma 1 is B is sent to 1. B comma 3 is B is sent to 3. C comma 3 is C is sent to 3. And the ordered pair notation in mathematics is special because we'll be able to graph that on a Cartesian coordinate plane if both our inputs and outputs are numbers, or real numbers. So we'll see a lot of ordered pair notation. Now, the relation that I just showed you, it turns out is not a function. It's a relation, but not a function. A function is a special type of relation. It's a relation such that any input can only be sent to one output. So if I give you and your neighbor the exact same inputs, you have to come up with the same answer. Same output. Value. That's what makes something a function. A function doesn't have options. We only have sort of one outcome if I give you an input. If I give you an input, there's only one right output. And that's different than what we had here. The reason that this relation is not a function is because B is sent to both 1 and 3. Okay. So anytime we have 2 or more arrows going out of a single input, we don't have a function in this notation. So this is that B going out to 2 different outputs. That's the indicator that we don't have a function here. Okay. And in arrow notation, that looks like B going to one value and B going to another value. In ordered pair notation, which is the one we're going to probably use most often, it looks like 2 ordered pairs with the same input value and different output values. So that's the thing we're going to focus on. We're going to figure out when a relation is a function or not, and we'll start with this ordered pair notation. So let's take a look at this first relation. We have 1, 2 as the first ordered pair, 1, 4 as the second ordered pair, 3, 6, then 5, 7, then 8, 9. How about this? We'll do thumbs up for function, thumbs down for not function. Function or not function? Yeah, not a function, right? Easy. Not a function in that first relation because the 1 goes to 2 and goes to 4. So because we have a repeated input value of 1 with 2 different output values, that's not a function. Let's look at this second relation. We have ordered pairs 1, 2, 2, 3, 3, 4, 4, 2, and 5, 3. Let's do thumbs up, thumbs down. Function or not function? Function. All right? Look at the inputs. 1, 2, 3, 4, 5. None of the inputs are repeated as inputs. Okay. It's okay that some of our inputs are also outputs. That's not a big deal. Okay. It's also okay that we have multiple outputs that are 3. That's perfectly fine too. Okay. If I give you and your neighbor the number 1, you're both going to end up here at the number 2. If I give you and your neighbor the number 4, you're going to both end up at the number 2. That's okay. As long as you end up in the same spot as your neighbor, given the same input, you're good to go. So that second relation, this relation here, is a function. How about the last one? Function or not? Yeah, function. Function. No repeated inputs. We have inputs of 0, 1, 2, 3, and 5. All of the inputs are different. So that's a function as well. So we have one that's not a function, and then the second and third relations are functions. Okay. Now, when we're dealing with ordered pairs, and that ordered pair notation, when I put in numbers, there's only a finitely many numbers I can write in my life, right? So if my domain has infinitely many values, then I have to create another way of writing relations where we can have infinitely many values in the domain. And the way we do that is we just write an equation with variables x and y. And then the solutions to that equation become the ordered pairs for different inputs and outputs. Okay. And the standard notation, we use x as the domain values, y as the range values. And the ordered pairs that make the equation true are the ordered pairs in our relation. Now, some of these will be functions and some of these won't be functions. We'll get to that in a second, but before we get to that, let's just take an example here. Here's a basic example. We have x minus 6y equals 10. And we can ask, does the relation contain the following ordered pairs? We have 4, -1. 2, 3. 5, -1, and 22, 2. I don't know. I'll get that. All right. So, does it contain those? How do I check? Well, I just plug those things in. I plug in 4 for x, -1 for y. Like I said, usually our domain is the x values, our range is the y values, okay? So when we plug things in, when we plug in ordered pairs are in that order, always. All right, for this class, they'll always be in that order. X first, y second. You could manipulate it otherwise, but for this class, it would always be x is first, y second. So I plug in 4 for x, I plug in -1 for y, and I see if I get a true statement. In this case, I do. So 4, -1 as an ordered pair is a solution to that equation. And therefore, 4, -1 is in the relation, right? That is described. So in short, we say it is a solution. So it would be in the relation that that equation describes. If we check that for 2, 3, I let x be 2, y be 3. 2 minus 18 is -16. -16 equals 10 is obviously false. So that is not a solution. The ordered pair 2, 3 is not a solution. And therefore is not in the relation. We can do the same thing with all of these. 5, -1, 5 for x. -1 for y. We get, is that 11? 11 equals 10. So 5, -1 is not, what is it? Not. That's what's going to happen. And then 22, comma 2. Plug that in. 22 minus 6 times 2. 22 minus 12, that is 'a solution. All right? Forgot to remove that thing. Over there. Okay. Pretty straightforward. And there's infinitely many ordered pairs for each equation that's going to make this work. In this equation, there's infinitely many ordered pairs that make this work. Not just these two, but lots and lots and lots of others, right? Infinitely many others. Let's do one more of those. I'll go over this one pretty quickly. Don't be thrown off. Hopefully you're not thrown off. By the order in which this equation is written, y squared is equal to 3x. And then we'll test 5, -2. We'll test -3, -3. We'll test 12, -6, excuse me, and 12, +6. In fact, why don't you go ahead, take a minute, do this one on your own. I'll do it on my own too. And I'll just say it is and not. I'll do that as I. All right, we'll go quickly through this. So when you plug in -2 for y, be careful that you plug in -2 for the y and the 5 into the x. We get 4 is equal to 15. So obviously this one is not a solution. Okay, -3, -3. Be careful about this one. When you plug in the negative, make sure you plug it in inside of parentheses and then square the thing on the outside. You'll get a +9 on the left-hand side and a -9 on the right-hand side. So that one is not a solution. Either. Be careful about that positive, negative stuff. 12, -6. If I plug in -6 into y, and then 12 in for x, I end up getting 36 is equal to 36. So this one is a solution, which means it's part of that relation. And then 12 +6 is also a solution. In fact, you get the exact same equation of 36 is equal to 36. So this is a solution. Make sense? By the way, at this point, we could say now we know this is not a function. This is the equation of a relation, which is not a function. We know it's not a function because one input goes to two different outputs. Right? So, interesting observation there. We'll see other methods as well. Which are a lot easier to determine functions, right? Based on the equations. The big one is graphing. Okay. We're going to take the Cartesian coordinate plane, or in other words, the rectangular coordinate system. And we're going to start graphing equations. If I want to graph a relation that is kind of interchangeable with saying graph an equation, I want to list out all of the ordered pairs that work, and we want to graph those on the XY coordinate system. It's called the Cartesian or rectangular coordinate system. It's called Cartesian. That's gets its name there from a guy named Descartes, who came up with a system. Rectangular, just because that you move in rectangular directions. The x-axis is the horizontal axis, so if we're moving in the x direction, moving left and right. The y-axis is the vertical one, so if you're moving in the y direction, you're moving up and down. Okay, up's positive, down's negative, right's positive x values, left's negative x values. So it's just two number lines that intersect. The point 0, 0 is the origin, and then each ordered pair we can graph on this Cartesian coordinate system. Okay. If we wanted to graph these relations, there's multiple ways of doing that. we have x minus 6y equals 10. Let's say we want to graph that. And we just saw y squared equals 3x. Say we want to graph that. If we were doing this by hand, what we would do is we'd go to a grid like this one, and then we'd plot a bunch of points. So for instance, we saw that the point 4, -1 was a solution to x minus 6y equals 10. We also saw that the point 22, 2 was a solution to x minus 6y equals 10. We could find a lot of other solutions as well and just plot those on a graph by hand, right? In fact, let me do that for just a moment. So if you're doing this, you don't have to do it by hand, but I'll do it by hand first. And you probably just wouldn't want just 2 ordered pairs or 2 points. You probably want a bunch of points to graph, so you can kind of get an idea of what this does. Another point would be 10, 0. Another point would be 16, 1. If you did -2, 2, that would also be another point. I won't check these, I'm just telling you what I'm kind of doing that in my head. You guys know how I'm doing that? Just plugging in 0, 1, 2 for y, and then solving for x. Okay, we'll get to that in a little bit. But trust me, here's your solutions. And so what you would do is you plot out on the rectangular coordinate system, you'd say, well, 4, -1 is 1, 2, 3, 4. -1. It's that point right there. 22, 2, way off the graph, what I'm drawing right now. I'll ignore that. 10, 0. In the x direction, 0 in y, places us on the x-axis. 16, 1, that'd be up here. Somewhere in there. I'm just approximating, obviously. And then -2, 2. -2 means we go in the x direction, left 2, and then positive. Is that right? No, I did -2, -2, right? I missed my negative sign right in my negative sign there. Excuse me. Sorry, -2, -2. Somewhere down here. And then if you plotted even more points, these aren't the only ones. You can plot lots and lots of points. You'd see that you get a straight line. The pattern is you get a straight line, and you just connect those dots. Again, I'm doing this in a sloppy way on the board, but you get the point. Okay. Did a little wave there, didn't I? Very bad, but. There's better ways to draw that. Okay? Straight line is what it should be. Somewhere. I didn't draw it very great, but that's the idea. And you can do the same thing for y squared equals 3x. You could plot lots of different points for that. And for that one, what you would end up with is something that looked, I won't do all the plotting of the points, but it looks like that. Okay. It looks like this arching. You guys know parabolas, it's a parabola pointed to the right. For this one. Okay. So you could plot points if you want. You can also utilize some graphing systems as well. And that's what that I want to do right now. Okay. You can also utilize some graphing systems to do that. And what you could do is you could use your TI-84. That's one option. Another option is use something called Desmos. I use this a lot in class.
That's what I'm using.
Using right now? All right. Yeah, I use that quite often in class. I don't need to sign up right now for this demonstration, but I will. X minus 6y equals 10. And if I type it in, you see we get the exact same line that I was talking about. And you can kind of zoom in and zoom out. You can see that it goes through all the points I was talking about. -2, -2. If I get close, let me change the settings slightly so you see all. So it goes through that point, goes through the point 10, 0, like I said. There's 4, -1. And then there's all these other points. There's infinitely many ordered pairs. These are all rounded to like 4 decimal places, if need be. And the one we couldn't draw, on Desmos, you can actually just grab the graph and move it over. So we didn't plot out the point 22, 2. But with Desmos, it's pretty easy just to grab the graph, pull it over. See that, in fact, it does go through that point of 22, 2. So, grab the graph, move it. You can zoom in, zoom out. A lot of nice things there. And then the other, y squared is equal to 3x. That graph, there's the one in blue. All right, obviously I drew it in red on the board, but same graph. And you can see what's happening with this graph. It's going through one point that's 12.6. And then if you go down on the bottom, it goes through another point of 12.6. And we said that caused our graph not to be a function. We knew that, right? We'll come back to that in a little bit. Now, this brings up something that we will see a lot, and it's basically the important part of this chapter, or not chapter, this section. And that's the idea of function notation. This is another notation, but this one only works when we have a function. We'll see why in just a little bit. But function notation is where we have, we'll call the function f, that's the most common letter to use, of x is equal to some expression. That expression will be an expression in x only, right? So it won't have any other variables other than x in it. And we say f of x is equal to the expression. Now, what that's equivalent to is saying our output of y is equal to that expression. We're going to get the same graphs. The variable x is the input. F of x is just the output of the function, which we've been calling y. So f of x gives us y values. And we find the corresponding y values by plugging in specific x values into the function. Most of you, I'm sure, have seen that before, and that's perfectly fine. So let's do this example. We have f of x is equal to 7x minus 2, and we want to find f of 2, f of negative 4, f of 0, and f of 11. So if I want to find f of 2, I just replace the x value, replace the input with the number 2 as my input. And what this says, this notation says, when we input a 2, we get out, well, this will be 12. 14 minus 2 is 12. Another way to say that is that we get the ordered pair to 12. That would be an ordered pair on the graph of y equals 7x minus 2, which is the graph of f of x equals 7x minus 2. Everybody get that? So graphing a function is just like graphing equations. You find some ordered pairs, see the pattern. You can also graph it using technology, and we'll see that as well. F of negative 4 well, I'd end up with negative 28 minus 2, so that is going to be a negative 30. Again, this is you input negative 4 into the function, and you get the output of negative 30. That's what it's telling us. Weird. And again, that's the ordered pair. Negative 4, negative 30. F of 0, 7 times 0 minus 2 is negative 2 or minus 2. And so that gives us the ordered pair of 0, negative 2. 11, 7 times 11 minus 2 is 77 minus 2 is 75. When you input 11, you get an output of 75. Ordered pair that you'd be graphing is 1175. Okay. So that's what we're doing with this function notation. We input values, get output. When I have this type of a scenario, function notation, it's really, really easy to generate out lots of ordered pairs. Because all you have to do is plug in different x values, and you can obtain the corresponding y values through the outputs. So when you have function notation, it's really nice because you can quickly generate out lots and lots of ordered pairs, lots and lots of points on that Cartesian coordinate system. You can do the same thing no matter what the function is, and the function doesn't always have to be called f. Other common letters for the functions that people use are h and k and g, things like that. If I have h of x is equal to x squared plus 2x minus 9, and I want to plug in a -4, I could do that. I'm just going to talk through doing that. We don't have to write it down if you don't want. But -4 squared plus 2 times -4 minus 9 would be a -1 on my calculator. So h of -4 would give me a -1. If we plugged in 2.3, I'd do 2.3 squared plus 2 times 2.3 minus 9. I'm just, again, typing this into a calculator. And I'd get 0.89. So in this case, h of -4 was -1. H of 2.3 was 0.89. You can do the same thing by plugging in -6, by plugging in 2. Did I have one? No, that's fine. Let's plug in -6. I'll plug in -6. Oh, we got a 15. What's going to happen when I plug in a 2? When I plug in a 2, I also get a -1. Okay. So I just want to point something out. We had h of x is equal to x squared plus 2x minus 9. When we plugged in -4, I got out a -1. When I plugged in 2.3, I ended up with a 0.89 as my answer. When I plugged in -6, I got a 15. And then when I plugged in was 2, I got a -1. Okay. By the way, is this a problem with functions or not? No, this is not a problem with functions, right? It's perfectly okay that -4 was sent to -1 and 2 was sent to -1. And remember, you can't have an input going to 2 different places, but 2 different inputs can converge at the same output. That's perfectly fine. But there we go. So we did that for f of x, we did some inputs for h of x. And again, most of this is just calculator work. Plug in the numbers, replace x by whatever numbers I'm plugging in, calculate. Now, on the other hand, we can work backwards too. I left that f of x on the board. I could say, well, if I have this f of x, same f of x as I dealt with last time, which is 7x minus 2. What is x if f of x is equal to 12? Or what's x if f of x is equal to negative 31? By the way, I think that can be also rephrased in a lot of different ways. Okay. You can say if f of x is equal to 12, what is x? Or when f of x is equal to negative 31. All of those mean the same thing, right? So you can rephrase that a lot of different ways, but in all of it, it means when the output is this number, let's find the input. Okay. Find the input when the output is this particular number. Okay. And the next question does that as well. I'm going to write this one on the board too, just so I don't have to flip back and forth. It says we have g of x, which is different, and it also gives us 12 and negative 31. So g of x equals negative 3x plus 42. And it says if g of x is equal to 12, what is x? If g of x is equal to negative 31, find x. I'm trying to phrase these in different ways that you can see in a normal homework problem or any of those things. Okay. So basically it says, here's the output. The output for any variable that I plug in is 7 times that variable minus 2. And we're saying, what's going to happen when the output is 12? So all I have to do is set this output equal to 12. Usually I'd set the one with the variable on the left, the constant number on the right. You can do it the other way as well if you like. 7x minus 2 is equal to 12. And then we're just solving a basic linear equation. Hopefully you all know how to do this. Solve basic linear equation. In this case, I added 2 to both sides. And then divide by the coefficient of 7. And I get an x value of 2. We could do the same thing for negative 31. I'd add 2 to both sides. That's 7x is equal to negative 29. And then divide both sides by 7. Negative 29/7 is a rational number, but it's not a whole number. It's not an integer. Okay. So negative 29/7 will have this ugly decimal expansion. Not super ugly. It does have a repeating pattern, but that repeating pattern, I don't know, negative 4.142857, and then repeats 142857. Okay. That makes sense? So a lot of times in Moodle, you will be asked to give an answer, and your answer might be something like negative 29/7. If it asks for the improper fraction, then you write negative 29/7 and you're done. If it says round your answer to 2 decimal places, then go ahead and round this to 2 decimal places, like negative 4.14. Be okay with that? Yeah. So a lot of the Moodle stuff will ask you to round, and so you just round it. Yes. Yeah, right. If g of x is equal to 12, what's x? Well, I'll go through this one quick too. Subtracting 42 from both sides gives negative 3x is equal to negative 30. Divide both sides by negative 3. We'll get x is equal to 10. G of x is equal to negative 31. Same process. Subtract 42 from both sides. We get negative 3x is equal to negative 73. Then you divide both sides by negative 3. One thing, you're going to get a decimal expansion that needs to either be rounded to a couple. Usually the typical Moodle stuff that I give says rounded 2 decimal places. That's usually what it asks you to do. All right. If it does ask you to write it as an improper fraction, then just leave it as 73/3. But what is that? 73/3? 24.33. If I round it. And oftentimes, when I round things, you'll see this symbol, which is the approximate symbol. It's like an equal symbol, but a little bit wavy. So it's the approximate symbol in that. But there you go. Any questions about that? Rounding stuff. Hopefully everybody knows how to do standard rounding. The number next to it is 5 or above. Move it up, 4 below, move it down. Keep it the same. Good. So let's go back. Now that we've looked at some function notation, let's go back and ask, when can some equation be written as a function? We looked at 2 equations earlier, x minus 6y equals 10, and then y squared is equal to 3x. So when can an equation be a function? That's the big question, right? If we're doing this algebraically, the way to do it is to say, well, if I want a function, I want to think of my equation being transformed into this function notation, where y is a function of x. That means my equation is going to have y as the range variable. So if I can write an equation that looks like y is equal to an expression in x, I'm good to go. Algebraically. Okay. Move that thing. So, algebraically, when do I have a function? Well, I have a function when I can set y equal to an expression in x. Then y is a function of x. I can just say y is equal to f of x, or y is equal to g of x, or y is equal to h of x. That's it. So if I can isolate y on one side of the equation all by itself, and then on the other side of the equation I can get some expression in x, I'm good to go. So if I look at my equation that I had earlier, which was x minus 6y equals 10, and I think about this algebraically, that's obviously a relation because it's an equation. It tells us a relationship. Can that equation represent a function with x as the independent variable? Independent just means input. And y is the dependent variable, that just means output. And then what if I did that for, what if I tried to do that for y squared is equal to 3x? Algebraic. I'll do them side by side because why waste time, right? So for this one, all I would have to do is try to get y by itself on one side of the equation. I'll try to get it on the left-hand side. I'd subtract x from both sides. That would give me negative 6y is equal to negative x plus 10. And then I would divide both sides by a negative 6. If I divide the left-hand side by negative 6, I get y. On the right-hand side, negative 1 divided by negative 6 is 1/6 x's. And then 10 over negative 6 is a negative 10 over 6. So now I have y is equal to an expression in x. So because I can get it this way, this is a function. It's just like having f of x is equal to 1/6 x minus 10 over 6. I didn't draw that. Right? It's the same function as that. So if I can solve for y, I get a function. Over here, we already knew that this is not a function, right? We saw 12/6 and 12-6 earlier. Were both points on that relation. So we knew it wasn't a function. The algebraic reason for that is because if I tried to take a square root of both sides, everybody know what I have to do?
Positive, negative.
Exactly. I have to do a positive or a negative square root on the right-hand side. So I get y is equal to a positive or a negative square root of 3x if I try to solve it. That's actually two equations. One of the equations, y is equal to positive square root of 3x. The other is the negative square root of 3x. That's going to happen when I have even exponents on y's. So this is not a function. Algebraic.
If that was a negative y squared, then it would be a function.
No, it still wouldn't, because I'd have to divide by the negative and then take the square root. Anytime I have a y, the squared is the problem, not the coefficient up front, if that makes sense. Yeah, the squaring it is a problem. We can do this for lots and lots of other equations as well. We can take things like x cubed plus 4 times y squared is equal to 16, or y cubed is equal to 5x plus 7, or x equals 4, and we can determine whether each function, or whether each relation represents a function or not. A function where x is the input, y is the output. In this first one, the y squared is going to be such that when you move everything over to one side and we just get a y squared on the left, I have the same problem that I just ran into. I take a positive and negative square root on both sides. And that kind of, I'm trying to get you to think, that kind of indicates anytime we have y squareds around, well, yeah, it's probably not going to be a function. Okay. How about x equals 4? Let's look at that. Can I solve that and make that y equals to an expression in x? No, I don't have y around, right? So that's not a function either. X equals 4 is not a function. Anybody know what the graph of x equals 4 looks like? Yeah, vertical line, exactly. Straight vertical line. So that is not a function either. On the other hand, weirdly enough, y cubed equals 5x plus 7 does not have that positive negative problem. Because when we take a cube root, you can take a cube root of a negative number, or I shouldn't say that. We can cube a negative number. So take negative 1 to the third power. You get negative 1. When you cube a positive number like 1 cubed, is still positive. So y to the third is equal to 5x plus 7. When you solve that for y, you would get y equals the third root of 5x plus 7, and you only get one option. You don't get a positive or negative option on that. So y cubed equals 5x plus 7 is in fact solvable for y and therefore a function. Now, solving for y is the algebraic approach, but I would say the quicker approach is if you have something that you can graph. Okay. Just like we saw with y squared equals 3x, we want to avoid ordered pairs which have the same inputs and different outputs. This means we can't have points on the same vertical line. And just like we saw in the last example, x equals 4 is a vertical line, x equals a is a vertical line going through having all x values that are a. Okay. And so if we have the graph of a function, I apologize. If we have the graph of a relation, we can test if it's a function using the vertical line test. If I have the graph and it passes through 2 points of a vertical line, then that graph is not the graph of a function. If every single vertical line passes through at most 1 point on the graph, then the graph represents a function. Right? So if a vertical line can go through 2 points, it's not a function. If all vertical lines only go through 1 or 0 points, it is a function. Makes sense. Questions? Now, in the book, they also introduce the concept of a one-to-one function. And I think that's probably the I don't know. They introduce it right now. So I'm going to introduce it right now. I'm going to talk about what one-to-one means. Okay. A function is one-to-one if it also avoids pairs where the output values match. Okay. And because we're doing the vertical line test is to see whether a graph is a function or not. You can also do something called a horizontal line test, which tests for one-to-oneness. If you have a horizontal line and it hits 2 points on the graph, then your relation is not one-to-one. So we'll look at these things graphically. I'll use Desmos today. We'll probably use graphing calculator later. These are harder to graph on graphing calculator because you have to solve for y on your graphing calculator or to graph. But we use Desmos today, and we'll decide based on the graphs if each graph represents a function and whether each graph represents a relation that's one-to-one. Okay. And so I don't have to flip back. I'm going to take a picture real quick. There we go. Good. So I can not forget what I do in the graph. Does that work? All right. You guys ever do that? I'm sure you do. All right. So we already saw this straight line, x minus 6y. Any vertical line is only going to go through that line one spot. So it is a function. We already knew that because we solved it algebraically, right? Also, any horizontal line is only going to go through this graph in one spot. Okay. If you can't see that, we could actually, let's just do that. Let's go x equals some number. And then we'll put in shoot. I gotta do it different. I get a slider for it. No, I don't want to use that either. Shoot. My bad. I'll show you how to do this. So, all right. Sorry. I had to go make a slider. Okay. So, x equals a is a vertical line, right? So what we can do is we can just move any vertical line through this, and you see the intersection of that vertical line with the line I had only intersects at one point. Okay, that's what I was trying to say. Horizontal line is going to work the same way. We can move through, only intersects at one single point for any horizontal line. So that means this is not only a function, but it's also a one-to-one function. X minus 6y equals 10 is a one-to-one function. If I do the other, which is y squared is equal to 3x, obviously it's failing the vertical line test because I can draw a vertical line right here that passes through 2 points. And we already solved it 12, 6, 12, negative 6 for 2 points as well. By the way, this is not a function, but is it one-to-one?
Yes.
It is one-to-one. All right. It's a relation that's one-to-one, only one output. Usually we don't talk about one-to-one relations that aren't functions in this class, but technically it passes the horizontal line test. Now here's why I took a picture, because I knew I'd forget. Let's go x cubed plus 4y squared equals 16. That was our you get this graph. Okay, that graph there in red. Obviously, it's going to fail a few vertical line tests, right? Over here, here. So this is not a function. Fails the vertical line test. Lots of different places. We actually predicted that because of the y squared thing, if you remember. Let's look at the Next equation, we had y cubed is equal to 5x plus 7. That actually passes the vertical line test. It might look like this is kind of going straight up here, but it's not. It is bending. You go zoom in enough. So there's no spot where it crosses more than one place. It's always crossing in just one spot. Okay. So this is a function. Is it 1-to-1? Yeah, this one's also 1-to-1. So this one's also 1-to-1. If you take horizontal line, hit the wrong button. Only passes through in one spot there as well. Every horizontal line passes through. So this is also a 1-to-1 function. Y cubed is equal to 5x plus 7. It's also 1-to-1. And then the last graph we were asked to do, x equals 4, fails the vertical line test because it is a vertical line. Okay. There is one vertical line, specifically x equals 4, that goes through that in infinitely many points. So fails the vertical line test. X equals 4. So x equals 4 is not a function in that case, or in any case. But. Now, you can also just be given graphs and not have the equation for those graphs. And you can do the same process. You can ask, is this a function? Is this 1-to-1? So let's go look at these graphs that are in example 13 and ask ourselves, do these represent graphs of functions? And if they are functions, are they 1-to-1? How about this first one, the one on the left? Function or not? Not, right? This is not a function, fails the vertical line test in lots of different spots. It also is not 1-to-1 because it fails the horizontal line test as well. Okay. The graph on the right, function or not? Is a function. Vertical line test passes. Okay. We pass the vertical line test. Every vertical line only goes through the point, through this graph in one spot. It looks a little bit like you might hit it twice here, but it doesn't. It's a little bit of a curve there if you zoom in far enough. So this is a function on the right, but it is not 1-to-1. It obviously fails a horizontal line test. So graph on the right is a function, but not 1-to-1. How about that graph on the left? Function or not? Yeah, that one's a function. The one on the left, vertical line test through that whole thing, works. Only crosses one spot. Is it 1-to-1? Yeah, no. There's horizontal lines that go through this in multiple places. Okay. On the right, function or not? Function. So on the right, that graph is a function, passes the vertical line test. Is it 1-to-1? Yes, it's also 1-to-1. As you move along, every horizontal line only goes through it at one spot as well. So the graph on the right is a function that is 1-to-1. The graph on the left is a function that is not one-to-one. Let's do the graph on the right here. Is that a function or not? No, fails the vertical line test. So the graph on the right is not a function. How about the graph on the left? Yeah, that is a function. Okay. There's some weird notation here. We have an open circle. That means it doesn't hit this point. Closed circle means it does hit that point. But if you draw a vertical line, every single vertical line crosses through at one point. And so that is a function. It's also one-to-one because if you draw a horizontal line, it's also crossing through at just one place. At most, some horizontal line like this one, the one at y equals negative 0.5, don't cross at all, but that's perfectly fine. So the one on the left is a function which is one-to-one, although it's a function that's broken into two different pieces. And we'll see in the next section, this is called a piecewise defined function because we have two different pieces that the function is broken into. Make sense? Good. All right. Well, that is it for the first section. For the first section, it's on definition of functions and one-to-one functions and what can be a function. Section 1-2, which we'll start today but we won't finish, is on domain and range of functions. And this is very closely linked and related to that first section. So we know what a function is. In the first section, we saw function is this relation that any input can correspond to only one output. So anything in the domain corresponds to a unique output in the range. Saw that? Good to go. These are the same two functions we looked at when we were deciding whether a relation was a function back in 1-1. Right? So these were, we've seen these before. I threw out the one that was not a function and kept the two that are. If I wanted to list out the domain and the range of these two functions, all I would have to do is list out all of the inputs and outputs. The domain is the set of inputs. So if I'm given all of the ordered pairs, I just have to look at all the ordered pairs and say, for instance, in this first function, the inputs are 1, 2, 3, 4, and 5. So that's what the domain is. 1, 2, 3, 4, 5. That is the domain. The set containing those numbers is the domain for that first function. The range of that first function, I look at the outputs. Those numbers are 2, 3, 4, and then I have a 2 and a 3 again. When you list out the range, you just list out 2, 3, and 4. You don't have to write out 2 again or 3 again. Now, I'm writing these in set notation. I'm not doing a great job on my squiggly set brackets. But set brackets are these ones, right? So the domain is the set containing all of those numbers. If I ask you to do something like this on Moodle, you just have to like type in the numbers directly, but you'll see when I write these on the board, I'll put set brackets around a lot of this. And that's all I'll do. Okay, so in that first function, the domain is the set containing all 5 of these numbers. The range is the set containing these 3 numbers. In the second example, if I'm looking at the domain and range, the domain is 0, 1, 2, 3, and 5. Is it okay that we don't have a 4? Yeah, that's fine. Doesn't matter. They don't always have to be in order. They can be any numbers you want. And then the outputs, it looks like 0, 1, 5, 6, and 10. So the range is the set containing 0, 1, 5, 6, and 10. These are what we call finitely defined functions because we can see finitely many ordered pairs. Obviously, we just got done talking about infinitely, or functions where we have infinite domains, where you can plug in basically any x value that you want and get out lots of different y values. Okay. That happens almost always with function notation. F of x is equal to an expression in x. And if we do have function notation, we can plug in almost anything we want. So we can plug in almost any real numbers, or almost any real number, get out infinitely many things as well. Right? So we want to start plugging in real numbers and getting out real numbers. But there are these weird mathematical problems that exist. Okay? Hopefully we know that if we're trying to plug in real numbers and get out real numbers, we might get an expression that cannot be calculated or that is undefined. Okay. And this is going to lead us into a domain error if I plug in a number and get something out that's undefined. Now in this class, the 2 problems that we're going to look for are dividing by 0 and then taking a square root or an even root of a negative number. Dividing by 0 is undefined on the real numbers. If I take 4 and divide it by 0, that's undefined. Again, on the real numbers. There are other number systems where we can kind of define that, but we don't do that in this class. In fact, if you take your calculator and plug in 4 divided by 0, it'll give you an error. It'll give you an error in your calculator. Okay. We also get an undefined on the real numbers if we're taking a square root of a negative number. And same thing, if you take a square root of a negative number on your calculator, you'll also get an error. It won't let you take the square root of a negative number. Now we'll see later on that we'll end up with complex numbers and imaginary numbers. We can deal with square roots and negatives. But for the purpose of graphing, we want to input real numbers and get out real numbers. We're not going to be able to graph something like square root of -4 on the Cartesian coordinate plane as a y value. Okay. So these are the two problems that we're looking for. We're looking for, in this class, dividing by 0 and square roots or even roots of negatives. So let's take a look at 3 examples. 3 different functions. And we'll decide what the domain of each of these 3 functions is. So now I'm just writing these on the board, obviously. Oh. All right. So if you look, we have f of x is equal to 4x squared plus 5x minus 6. Okay. Are we ever going to divide by 0? No. There's no division by a variable. Right? No dividing by any variable. This is x squared, that's multiplying by a variable. That's fine. We can multiply by 0, that's just fine. 0 times anything is 0. But dividing by 0 is a problem. So we're not dividing by 0. And are we ever taking a square root when I'm plugging a number in? When I plug a number in, do I ever take a square root? No. I square it, that's fine, but I don't take a square root. So there's no problems here. I'm never going to get any problems by plugging in a real number. I'll always be able to calculate out this right-hand side, no matter what I plug in. So that means the domain is all real numbers. By the way, if you're looking on in the book, or if you want to save yourself some time on writing, there's a special way of writing all real numbers. And that's just a capital R with a double line on the left-hand side. When you pick out your answer, I don't know, some answers may say all real numbers, others may have that symbol for all real numbers. You guys seen that symbol before? Very good. And I always write it, when I'm writing it freehand on the board, I write it like that. In some type scenario, it'll look like a double, and then it'll also double the other 2 sides as well, right? The other parts. That's harder to write. So most math people, when they write on the board, this is the official one. You're writing it on the board, but in some printing scenarios, like if you look at for the symbol for all real numbers and you're doing it in Microsoft Word, it looks more like this. Like double lines all around. All right, for g of x, for g of x, we don't have any square roots around, but we do have a denominator that could be made to be 0. So we would have a problem if or when that denominator was equal to 0. Add 5 to both sides. We'd have a problem when x is 5. Okay, get that? If I plugged in a 5 for x, I get 22 over 0. Which is undefined. You don't have to write this down if you don't want. I'm just explaining. So if I plugged in 5, I get 22 over 0. Now be careful here. The domain is everything we can plug in. X equals 5 is a thing I can't plug in. So the domain is all real numbers except for 5. Or sometimes people would say except x equals 5. Right? There's different ways you can linguistically say that, but it's everything except 5. That's the point. So do you say all real numbers except 5 or all real numbers except x equals 5? That's fine, either way. Or you could just do this symbol. All real numbers except x equals 5, or all real numbers except 5. Everything but 5 works. There's other fancier ways to write the domain. You can use interval notation if you want. You can use set notation if you like. We don't do that in our class. In our class, when you're asked to do a domain, it's going to be a multiple choice thing. It's a drop down, and one of the options is going to be 5, I'm just telling you. And that'll be the wrong option. Another option will be all real numbers except 5. That'll be the right option. Okay. Yeah.
Interval notation is when it's like negative infinity.
Yeah.
Okay.
Yeah, so the interval notation, again, we're not going to worry about that for these types of problems, but the interval notation will be negative infinity up to 5, and then union from 5 up to positive infinity, with parentheses on there because you can't touch 5. So that would be the interval notation. Again, we're not going to worry about that. We will worry about interval notation, just not in this section. We'll deal with interval notation, just not in this section. Now, the last function here is h of x. We're not going to be dividing by 0 anytime, but we would get a problem if what's underneath our square root is a negative. Now, there's kind of 2 ways to go about this. You can either say the problem is going to happen when x is this, or you can say this square root will work when x is this. Okay, I'll do both options here. I'll do the domain is when the thing underneath the square root is greater than or equal to 0. So this is my first option. Then I'd add 11 to both sides to make that clear. So as long as x is 11 or above, I'm good. When it's 11, I get square root of 0. I can take a square root of 0. I can take a square root of a positive number. That's perfectly fine too. So that's probably what I would do. As I'd say, the domain is all x's where x is greater than or equal to 11. Okay. All x's such that x greater than or equal to 11. You can write that a little bit fancier, but for right now, we'll just stick with that notation. Okay. You could have also done this by addressing that we're going to have a problem when x minus 11 is negative. Negative just means less than 0. And then I'd add 11 to both sides. We'll do some more solving of inequalities, but we get a problem when x is less than 11. And then you'd have to, in your mind, say, well, we have a problem when x is less than 11, then our domain is all the other numbers. So you could have done this option for finding the domain, just started with all the ones that work. Or you could have said, what are the ones that don't work? And then translated that into all of the ones that do work. Pretty straightforward. These are the two big ones where you get problems in this class, dividing by 0 and square root of a negative, or any other even power would have also been the exact same, right? If I had a fourth root of x minus 11, I also can't take a fourth root of a negative and get a real number out. Same thing with a sixth root, or an eighth root, or a 10th root. All even roots work the same way. I can't take an even root of a negative and get a real number out. Now, if I had a third root, whole different story. Perfectly okay to do a third root of a negative. But any even root can't plug in negatives into that and get a real number out. So it wouldn't be more. All right. Other questions? Anything right now? We will continue on with this material next class. Obviously, if wrong button. Okay. If you want to try some things, go ahead and try some things. You can kind of see where this is going. Yes. Oh, shoot. I wanted to show you before you left, just 1 minute, what this is looking like on Moodle. It's going to say domain is, and then you see your options. Okay? Domain is, and then you see your options. Okay. And so that's how the questions are going to be phrased on Moodle for these types of problems in this section. Okay, domain is, and then drop down and you pick the appropriate one. Okay. All right, well, I will see all of you Thursday. Okay, see you then.